Okay, where we had left off last time, we had talked about what was called an aldol condensation. So before we start with today's lecture, which are just some other condensation reactions, let's review the one that we did yesterday. We said that if you were to take, for example, a ketone, and we'll use acetone, and react it with itself, in the presence of a base, what we get is a condensation reaction. And here's what happens. And I'm just going to draw these into steps. The first thing that happens is an alpha hydrogen gets lost. Okay? Notice in this case, all the alpha hydrogens are the same. Then the second step in this reaction is that one of the enolates, the enolate that was formed, goes and acts as a nucleophile, kicking this pair of electrons up. Then this becomes protonated because remember, if there's OH minus in there, there's also H2O in there. Okay, because it's just a aqueous solution of sodium hydroxide that we use. So the next step is protonation. So we can draw that product. And again, whenever I draw this product, I always draw it so that the C double bond O is over here. So notice that's this one and this one. Here's my CH2 hooked to this C. Now this C is this C. Notice we have two CH3s here. And we get an OH. I always draw the OH up. Now this class of compounds, and we discussed this in the last lecture, is called a alpha beta hydroxy ketone. We said that if you heat this compound, it can lose water. And let me redraw these hydrogens up and down. So if we draw those hydrogens up and down, we lose a water, and we lose the OH from the beta carbon and the H from the alpha carbon. And we end up with a compound that looks like this. And we said, and let me go ahead and put this H down here to the side somewhere. We said this compound was called an alpha beta unsaturated because the double bond is between the alpha and beta carbons. So this is what's called an alpha beta unsaturated ketone. Now listen carefully. In the reaction of ketones with themselves or aldehydes with ketones or aldehydes with themselves, okay, we always get either a beta hydroxy ketone or an alpha beta unsaturated ketone. That was called the aldol condensation reaction. What we're going to look at now, though, is we're going to look at a different condensation reaction. And this is on pages 1, 2, and 3 of section 3 and page 4. Okay? So we're going to look at a different condensation reaction. We're going to look at, oh, excuse me. We're going to look at a condensation reaction between esters. Okay? Now, last time we said that the pKa of a ketone hydrogen was about 20. It turns out that the esters are not nearly as acidic. And here's why. If we look at an ester, we have this kind of structure. Now, if we look at that ester, we could draw this resonance structure where I move this pair of electrons down and this pair of electrons up. Now notice we have a positive charge there and a negative charge there. So this resonance structure isn't as important as we would think, but it is somewhat important. There's charge separation, but it is a valid resonance structure. So what this does is it changes the acidity of the alpha hydrogens, okay, making them not as acidic. So if we were to look at two reactions, for example, if we were to look at the reaction of a ketone. So let's just look at acetone. And we were to look at its reaction with, let's say, a base. And I'm going to choose OCH3- as my base this time. Notice again what that base does. It pulls off one of the alpha hydrogens in an acid-base reaction. Now, it turns out that the pKa of this is about 20. Now, if we did the same thing with the ester, notice how I'm going to write the ester. I'm going to write it this way. Now, notice these are alpha hydrogens. These are the hydrogens that are alpha to the carbonyl. Notice these hydrogens over here are not alpha to the carbonyl. They're on the oxygen side. So these are the hydrogens that we're talking about. Now, if we take and react this with OCH3-, notice we get the same structure. Because of the resonance stabilization of the electrons in this one, this compound turns out to be less basic. It has a pKa of 24. So notice this compound, the ester, is 10,000 times less basic than, or excuse me, less acidic. I'm sorry, I'm saying basic. Less acidic than the ketone. So what you need to know from this is that ketones and aldehydes are more acidic than esters, okay? Now, listen carefully. What can we say about this? The alcohol has a pKa of about 16. So notice these, whenever we look at this, this would be the acid, this would be the acid, okay? There's the base and there's the base. So the reaction goes to this is the strong acid, this is the weak acid. So this is an equilibrium that lies back in this direction in both cases, okay? But it is an equilibrium, okay? So what we're going to say is that we're going to now look at the reactions of this. So all we've done up to now is we have said, not only can we lose the alpha hydrogen off of a ketone, we can lose the alpha hydrogen off of an ester. So let's look at the reactions of esters whenever they undergo these condensation reactions. So again, we had the condensation reactions already of the ketones. Now let's look at the esters. So what we have here is we have this compound here. Now there's one difference in the reactions of esters. The base that has to be used, and this is important or you'll lose points on the test, the base that has to be used has to be the same as the ester part of the ester. So notice we have an ethyl group here attached to the oxygen. That must mean we use the ethoxide ion here. If we had had a methyl group attached here, we would have used the methoxide. If we would have had a phenyl group here, we would have used the phenoxide. Okay, so whatever group is here has to be the base that's used. Now remember, whenever I only give you one compound, that means it's going to react with itself. So the first thing that's going to happen here is this is going to deprotonate the alpha carbon. Now watch what happens next. This reacts with another molecule of itself. And again, this behaves as a nucleophile. So what happens is this goes in, backside attacks here, kicking up the pair of electrons. Exactly the same thing it did whenever it reacted with the ketones. Now the product of this reaction is this. Now I'm going to try to draw this kind of so I can see everything. I'm going to keep this piece first. So notice what I'm going to do. I'm going to write CH3, C double bond O. Now, that's attached to, well, it's not a C double bond O now, it's a CO minus, because notice that pair of electrons got kicked up. We have the OCH2CH3 still attached. Then now this carbon is now hooked to this carbon. So I'm going to write the rest of this. CH2, C double bond O, O, CH2, CH3. So does everybody see what I've done? This backside attack kicked the pair of electrons up and I just rewrote the structure. Now what happens is this pair of electrons can kick down because this is a good leaving group. Notice when this leaves, it regenerates the base that was needed to do the reaction. So now I'm just going to repeat the process. CH3, C double bond O, CH2, C double bond O, O, CH2, CH3. And then the other product, again, is the OCH2, CH3 minus. And again, that goes back and does the reaction again. So notice what the product is of this ester condensation. This is called the Claisen condensation. Notice what the product is. Here's the ester group. Here's the keto group. Since the ester group has a higher priority than the keto group, this is what is referred to as a beta keto ester. Notice the keto group is on the beta carbon to the ester. Notice we go alpha, beta. So this is a beta keto ester. So whenever you condense two ester compounds together, you get a beta keto ester. So as you're writing your notes up for the test, that's something that's important to realize. Two ketones, remember, gave you a beta hydroxy ketone or an alpha beta unsaturated ketone. Now we find that two esters give us a beta keto ester. And again, it's very, very straightforward. The only difference is here, once we got to this step, instead of protonating, this pair of electrons could come back down because in this case, we had a good leaving group. So again, notice the product is a beta keto ester. Now we want to look at, again, the cyclization reactions. This is called the Diekmann condensation. It's exactly the same reaction, but it's where the two ester groups are in the same compound and a ring is formed. So we've seen this before whenever we did the aldol condensations that we formed rings. So this is exactly the same thing. So let's look at a reaction. CH3O, C double bond O, and it's got 5 CH2 units in the middle of it. and then another C double bond O, OCH3. Now, the base that we're going to react this with, again, is going to be OCH3 minus. Whenever you have esters in the compound or esters in the reaction, the base has to be the same thing as the ester part of the compound. So notice this is an OCH3. The base must be OCH3 minus. Now, let's do exactly the same thing. Step 1 is removal of an alpha hydrogen. Now, again, it makes no difference which alpha hydrogen you take because this molecule is symmetrical. If you had two different types of alpha hydrogens, you would get a mixture of compounds and the reaction is not as useful. So let's go ahead and rewrite this. And I'm going to take this alpha hydrogen off. Now, what happens next? This reacts with itself, kicking this pair of electrons up. Notice the only difference in this reaction is that both ester groups are in the same compound. Whenever I do that, notice I have a 1, 2, 3, 4, 5, 6-membered ring. And again, the only reason I'm numbering these is so that I can keep it straight whenever I draw my picture. So now I have a 6-membered ring. Okay, in my notes I drew it sideways, so let me draw it sideways on the board. It makes no difference, so I'll try to be consistent with my notes. Okay, let's number these. Okay, so notice the number 1 carbon is here. 2, 3, 4, 5, 6. And again, it makes no difference how you number. So what do I notice? On the number 1 carbon, I have what? An O minus and an OCH3. Then on the number 6 carbon, I have a C double bond O, OCH3. So again, by keeping these numbered, you can see what's attached. That's especially important if there's attachments here in the middle so that you know which carbon it goes on. Now that I've got that drawn, I'll erase my numbers because I just really numbered those arbitrarily so that I could get this far in the structure. Now notice again, since we have a negative charge there, a pair of electrons kicks back, kicking the OCH3 out. Again, notice that this is easily explained just following the flow of electrons. And notice the product of this then would be what? And now I have a double bond here. If I've done this correctly, the product should be a beta keto ester. There's my ester carbon, alpha, beta. Do I have a beta keto ester? If I don't, I know the answer is wrong. So that's an easy check to see if you're doing the reaction correctly. Now, what we've looked at up to now then is a reaction between two esters. But in the cases that we've done so far, the esters have been the same compound or the two ester groups have been in the same compound. Now we're going to look at what's called a crossed Claisen condensation. This is where the two esters are different from one another. We did the same thing with the aldol condensation. So in the cross-Claisen condensation reaction, we have two esters, but only one of them will have alpha hydrogens on it. So let's look at the reaction between this and this. And again, notice the base is OCH3 minus. And both of these esters need to have the same group out here. Notice this is OCH3 and this is OCH3. If you don't, what happens is you get transesterification reactions, which we talked about in chapter 21. So all of the ester groupings need to be the same, and the base needs to be the same as the ester groupings. Now notice this is the only one with alpha hydrogens. Notice these hydrogens are attached to the alpha beta carbons. So only the alpha hydrogens react. So the first step is going to be loss of the alpha hydrogen. Notice this is not really that hard if you just follow your steps. And some of y'all on your note cards will write those words out. Step 1, loss of the alpha hydrogen. Now notice what happens in step 2. This comes in, backside attacks, kicking that pair of electrons up. Now I'm just going to rewrite that. Again, I'm going to rewrite this piece first so that my ketone group is on this side. So there's my O minus. I'm going to write my OCH3 down here, and then I'm going to hook it to this piece. So there's my CH. I'll put my phenyl group either up or down. I'll put it up out of the way. And I like to keep my ester group in line on the same chain. So notice I have this. So notice what happened was this carbon came in and backside attack here, keeping the electrons up. Here's this part of the molecule. Here's this carbon here with its phenyl group either up or down, off out of the way. And then notice the rest of the ester group over here. Then what happens is this kicks back down, kicking this off. If I've done this correctly, I should have a beta ketoester. Notice here's my ester group, alpha, beta. Okay, so it's not any different than what you've seen before. Now we're going to look at one new reaction. So we've looked at the reaction of two ketones with each other, and we've looked at the reaction with two esters with each other. Now we're going to look at the reaction of a ketone with an ester. Okay, we're going to look at a reaction of a ketone with an ester. Now, we said earlier that if we had these alpha hydrogens on a ketone, they have a pKa of about 20. We said the alpha hydrogens on an ester, the pKa was about 24. So if you have a reaction of an ester and a ketone, and both of them have alpha hydrogens, who's going to lose the alpha hydrogen? The ketone, because it's much more acidic. It's 10,000 times more acidic than the ester. But normally we try to do these reactions again where only one of the compounds has an alpha hydrogen. But if both of them have alpha hydrogens, the alpha hydrogen on the ketone or aldehyde will be lost. Once we know that, the reaction is no different than what we've seen before. The product will be different, but the reaction is not. Let's take the reaction of acetone with methyl benzoate. Now notice again, we've got alpha hydrogens on the ketone. We don't have any alpha hydrogens on the ester. Remember, these are not alpha hydrogens. They're attached to the oxygen side. The alpha hydrogens has to be attached to the carbon that's attached to the C double bond O. So again, since we have an ester in here, the base that we have to use is this base. So what's step one? Step one, again, is loss of an alpha hydrogen. So notice what I'll do. And again, it makes no difference which one we lose, okay? In my notes, I lost the hydrogen on this side. Now what's going to happen? Just like in all of these cases, this acts as a nucleophile doing a backside attack, kicking the pair of electrons up. So again, notice what I'm doing. I'm rewriting the steps so I don't get lost. There's the CH3, C double bond O, CH2. Notice here's this C. I'm going to write the O up and the OCH3 down, and the phenyl group over here. Now, the reason I wrote it that way, notice this oxygen again now is negative because the pair of electrons came up. When the pair of electrons comes down, kicking off the OCH3 group, notice what the product looks like. Notice the class of compounds. Okay, notice this is a ketone group and this is a ketone group. This is a beta diketone. Notice one of these is going to be the one you start from and the other is going to be alpha beta. So notice the product of this reaction is a beta diketone. So whenever you get to these compounds and you're looking at the reactions, it's important to know that you can get 4 different classes of compounds. 2 ketones or 2 aldehydes. I'm using the words ketones and aldehydes to mean the same thing. 2 ketones undergo an aldol condensation to either give you a beta hydroxyketone or an alpha beta unsaturated ketone. 2 esters gave us a beta ketoester as a product. Notice that the reaction of an ester with a ketone gave us a beta diketone. And if it were me and I were writing these notes out, I would make certain that I wrote those pieces out whenever I was making my note card. And I would probably write those out in words because it's going to help you. So we can easily determine what the product is if I've given the reactants. Now let's go to page 6 and see if we can look and see what go the other way in this reaction. Suppose I asked you on the test, to tell me what reacted to produce that. Now listen carefully. The first thing I would do if I were given that question is I would say, what kind of compound is that? Do you see it's an ester, alpha, beta. It's a beta ketoester. So the first thing I would know then is that my reaction is going to be what? 2 esters reacting together, because isn't that what happens? Now watch what I'm going to do. And this is what we've been doing in the past when we did this. We look at the bond between the alpha and beta carbon, and I'm going to break that bond. So isn't that the new bond that was formed whenever the compound was formed? So I'm just going to break it. And I'm going to add an H to the alpha carbon. And then I'm going to add something to the beta carbon. Now, normally what we add is OH. But remember, we said that when we had these ester groups, they all had to be the same. So since this was an OCH3 group, I'm going to add an OCH3 group there. Okay, because they have to stay the same. So we're going to break that alpha beta bond, adding a hydrogen to the alpha carbon, and then whatever other piece is necessary to make it the correct ester. And then I can redraw that. And then notice I have 1, 2, 3 carbons. 1, 2, 3. And then off of that carbon, I have a ester group. And you can draw this as a line angle like I did here, or you can draw it, showing the CH2, CH2, CH2 groups. So notice what happens when you have compounds that look like this. They react with themselves, okay? Notice in this case, both ester groups were in the same compound. So if you have to break these molecules apart, it's very, very simple to do. Let's look at one more of these. Still on page 6, I have we're trying to make the following compound. CH3, CH2, C double bond O, CH, CH3, C double bond O, O, CH2, CH3. Again, notice this is a beta keto ester. So again, what's going to happen is there's my ester group, there's my keto group, alpha, beta. I'm going to break the alpha beta bond, adding a hydrogen there, and adding my ester group here. And notice again, I added the same thing that was already there. And then you can see that these two compounds are the same thing. So notice this reaction is just a condensation of this compound with itself. So the reaction would just be this. This is what I would want to see on the test. If you wanted to write this plus another one, that would be fine. But if you only see it one time, that means it reacts with itself and there's two of them there. So again, very, very straightforward. Now what we're going to do is go over to and look at just another series of reactions. And the reason that we're going to look at these reactions is they have such an importance in chemistry. They allow you to make a class of compounds that otherwise would be very, very difficult to make. So before we can look at the next two reactions, we need to talk about the acidity of compounds. And I like page 7 of the notes because page 7 really, when you see this presented, if you understand it, then it makes sense of what you're doing. If you can understand this, then you really have an understanding about acidity and basicity of these carbonyl compounds. So as we go through this, just pay attention and see if it all makes sense to you. We said that this compound, that this alpha hydrogen, the pKa of these hydrogens was about 20. Then we said if we had an ester okay, and it doesn't matter whether it's an ethyl or methyl group, that these hydrogens had a pKa of about 20. These had a pKa of about 24. So we said the ketones were more acidic than the esters. Now, I'm going to put another compound on the board, and I want you to tell me what is the most acidic hydrogen in this compound. Notice these hydrogens are not only alpha to this carbonyl, but they're also alpha to this carbonyl. These two hydrogens are between two C double bond O's. That makes them very acidic. These have a pKa of about 11. Notice these over here would be about 20. Okay, so because they're between the two carbonyls, and you can draw the resonance structures for those if you want, they're much, much more acidic. They're even more acidic than water, okay, which has a pKa of 15.7. Now, if we look at the next compound, notice what's different about it. These are still alpha to two carbonyls. But notice up here, one of the carbonyls was a ketone and one of the carbonyls was an ester. In this compound, both of these compounds, or both of these groups on the two ends, are ester groups. So again, because ketones are more acidic than esters, a alpha hydrogen that's between two esters is less acidic than one that is between a ketone and an ester. So this has a pKa of about 13. So what we're going to say is these hydrogens that are between a ketone and an ester group and between two ester groups are much, much more acidic. Now you need to know the name of this compound. Now the name is actually not correct in my notes. This is called acetoacetic acid, and we need to add the ethyl ester, because notice the ester group over here has an ethyl group on it. Now this is called malonic ester. Okay, because notice it has two ester groups on it. Now listen carefully. You need to know the names of those two compounds. So on your notes, you're going to write this structure and write the names of them. You need to know those, because on the test, I'm going to give you a question, and I'm going to say, in the malonic ester synthesis, do something. Then you know that you're going to start with this compound. Or either I'm going to say, in the acetoacetic acid synthesis, do something. And you know you're going to start with this compound. So you need to know the structures of those two compounds with the names of them, because I'm not going to give you the formula. I'm just going to give you, using the malonic ester synthesis, do something. Okay, so you have to know what malonic acid or malonic ester is, or the acetoacetic acid ester is. Okay, so you have to know those structures. So now let's look at the usefulness of these two reactions. And this is on page 8 and 9. And you're going to see one of these two reactions on the test. Now here's the usefulness of it. Let's look at the malonic ester synthesis first. So if I've got the malonic ester synthesis, we're going to start with that compound. Okay? Whoops. Now watch what we're going to do. We're going to treat this with a base. What base will I use? Since I have the ethyl group on the ester, I have to use the ethoxide ion as my base. What do you think that's going to do? It's going to deprotonate the hydrogen. Okay, so if I do that in step 1, notice what it does. It deprotonates that. Now, if I add an alkyl halide to that in step 2, now let's pretend that alkyl halide is primary. What's going to happen? This is going to act as a nucleophile, a backside attacking the R group and kicking out the halogen. So what does that do for me? Puts the R group on there. Now I could stop at that point if I wanted to, okay, and only replace one of the hydrogens with an R group. But what if I then added some more base? I can deprotonate this again. And now I can add either the same alkyl halide or a different alkyl halide. So I can put an R group that's different on there if I want to. Now that's not too amazing in itself. But the next step is, if we then take this and acidify it, a reaction that we learned in chapter 21, if you take an ester and acidify it, it turns the ester into the carboxylic acid. Now I'm going to rewrite that now. And I'm going to put my R groups down here off to the side. So we turned both esters into carboxylic acids. Now, the next reaction is we're going to heat this now. And what heat does is you lose a CO2 molecule. So one of these CO2s goes away. And the product is this. Now, that doesn't look too impressive. It really does not. Okay, whoops, I left out a carbon, sorry. Yeah, I left out my carbon. Better, yeah, can't have 6 bonds of that. That doesn't look that impressive, except what you've done is you've taken acetic acid and replaced 2 of the hydrogens with R groups. This allows you to make a whole series of compounds. You could put any 2 R groups on here. Now, before we go away from this reaction, notice what happened. Deprotonation, alkylation. Deprotonation, alkylation. Acidification that caused hydrolysis reaction with water to form the carboxylic acid, followed by decarboxylation. We lost a CO2 group. So the product of this reaction will always be a substituted acetic acid. Now, before we go away from this reaction, though, I want to show you something that's pretty amazing, okay? I want to show you the mechanism for this step, because this step is called decarboxylation. We have lost a CO2 molecule. Now, in the body, there are enzymes called decarboxylase enzymes. Remember, enzymes always end in ASE. The decarboxylase enzymes, guess what they do? they cause the molecule to lose a CO2. How does this reaction occur? This is what I want to show you. So here are the steps for the mechanism. Again, or the steps in the reaction. We can add only one R group or we can add two. We can stop the reaction with just one, but notice in my example, I did two. Now I want to show you that step. Now, for those of y'all, again, who are going into a field where you're going to have to understand how biological molecules react, this is really an interesting, it's just interesting. Okay, so here's what we're doing. We're taking we're taking a H, O, C double bond O, C with two R groups attached. And we're going to lose one of those CO2s, and it doesn't matter which one. Okay, so I will lose the one on this side, just to show you that it doesn't matter. Notice the product of the reaction is a substituted acetic acid. Now, how does that reaction occur? Watch what I'm going to do. I'm going to try to draw this, okay, and I'll probably have to redraw it a couple of times because I usually mess it up. There are my two R groups attached to that carbon. Off of this carbon, I have a C double bond O, OH. Now notice on the other side, I also have a C double bond O, OH. Now notice how I've written that structure. Okay, I've written it in a ring structure, and it actually exists in this ring structure. Normally, this would not be a good conformation for this molecule, because in this conformation, what's true? The molecule that is sterically bumping into each other. But this hydrogen can hydrogen bond with that oxygen. So this forms this six-membered ring intermediate. Haven't we seen those before? Okay, so when you have these dicarboxylic acids, okay, they like to form this cyclic conformation. Now notice what's going to happen. This pair of electrons is going to move over to here. This pair of electrons is going to move to there. And this pair of electrons is going to move to there. Haven't we seen this type of mechanism before, this movement of electrons? Wasn't this what we saw in the Diels-Alder reaction? Even though this isn't a Diels-Alder reaction, notice the flow of electrons is the same. Now watch what happens whenever we draw that picture. The C, and I'm just going to keep the atoms in the same configuration, even though we know that's going to be linear. There's how I lost my CO2. Now notice what's left in this picture. We have our C with our R group and our R prime group doubly bonded to the other C, which has an OH here and an OH here. Okay, so notice what we have. We have a structure that looks like that. And then this just does an enol keto tautomerism, okay, where this pair of electrons comes up here and this H comes down here. Haven't we seen keto enol tautomerism before? And notice what the product is. Our substituted carboxylic acid. The key thing for you to realize is this, and I will leave this reaction with the following statement. Whenever molecules can form conformations that form ring structures that are 5- and 6-membered rings, where one part of the molecule is hydrogen bonding with the other part, that is a very stable conformation for the molecule, and it oftentimes explains the reactivity. And again, in biological systems, these decarboxylation reactions occur very nicely. What do the decarboxylation enzymes do? They hold this molecule in these conformations. So in chemistry, what do we have to do? We have to heat it to get it into that conformation to get it to react and lose the CO2. Well, we can't heat something to 200 degrees in the body or 120 degrees in the body. What do we have to do? We have to add an enzyme that holds it in this conformation. The reaction occurs, the CO2 is lost, and then the enzyme goes back to grabbing another molecule. So the body, instead of heating the reaction to drive it to completion, it uses enzymes to drive the reaction to completion. So a lot of the mechanisms, and I hope that that's something you've gotten out of this course, a lot of the mechanisms that occur in organic chemistry are going to be the same mechanisms that you're going to see in biochemistry, except the difference is the body uses enzymes where we often use concentrated acid or this strong oxidizing agent or reducing agent. We use some kind of other compound. So notice the product of the acetoacetic acid reaction, or excuse me, the product of the malonic acid reaction, malonic ester reaction, is a substituted acetic acid. Now, looking at the next reaction, starting with the acetoacetic acid, the same thing is going to happen. So we're going to start with this compound here. Now, sometimes we write chemists get lazy and write this ethyl group just as ET, okay? If you want to do that on the test, that'll be fine, or you can write it out. Step one, again, is we're going to treat this with the unprotonated alcohol, so that is the base. And what does it do? Whoops, oh, that's not an oxygen, that's a CH2, sorry about that. Again, this is the most acidic hydrogen, so we deprotonate it, then we treat it with an alkyl halide that does what? Puts the R group on there. Again, we can do this twice, or we can stop with just one alkyl halide. So in this example, I stop with one alkyl halide. Again, when we treat it with acid, what the acid does is it destroys the ester, so we end up with this compound here. It turns the ester back into a carboxylic acid. So what do we have? A beta keto carboxylic acid. And using the same cyclic mechanism we saw before, when we heat this in step 4, we lose the CO2, and notice what I get. Now in this case, notice the product is different. We get a alpha substituted acetone. This is acetone. So notice what happens. One of the R group or one of the hydrogens gets replaced by an R group. We can also replace 2 of them. But this is a nice reaction. If we were to replace 2 of them, we would replace them on the same carbon. Because notice this carbon was never affected because it was not nearly as acidic as this carbon, the hydrogens on this carbon. Okay? So again, we're either going to get an alpha substituted or an alpha-alpha disubstituted acetone. Okay? Very, very straightforward. So again, you're going to see one of those 2 reactions on the test. Now that pretty much finishes up all of what I would call the normal reactions. We've got two more reactions that we need to cover. And these two reactions are just weird. Okay, let's just simply say that. They're weird reactions, but they're very useful reactions. And what they do is they illustrate many of the concepts that we've just learned. And you're going to see one reaction on the test of one of these two. The first one is called the Michael addition, and the second is called the Robinson annulation. Now, there's a trick with both of these reactions. The Michael addition reaction. The Michael addition reaction starts with an alpha beta unsaturated ketone. So if we have this compound here, and we just got finished learning how to make this compound. Remember, we learned how to make the alpha beta unsaturated ketone by reacting two aldehydes or two ketones together, or two ketones and aldehydes, and then dehydrating it. Now, this one happens to have a name. This is a methyl group. This is called the vinyl group. This is called methyl vinyl ketone, MVK. It's one of the most highly used compounds in organic chemistry. It's the starting material for many industrial processes. Okay, so when you see the abbreviation MVK, for those of y'all who are going into an industrial field, it stands for methyl vinyl ketone. We would probably name it using our IUPAC name, but that's the common name for this compound. Now, if we attach this or attack this compound with a nucleophile, nucleophiles can attack in one of two ways. The first way is called 1,2 addition. And it's the way that we would normally think a nucleophile would attack. The nucleophile would backside attack the carbon, kicking the pair of electrons up. We've seen that reaction many times. So the product of this reaction is the following. With our nucleophile down here. Then when we protonate this, notice what happens. We put an OH there. Notice the nucleophile and the hydrogen attacked or attached in a 1,2 location. 1, 2. That makes perfect sense. But what can also happen in this reaction is, instead of getting a 1, 2 attachment, you get what's called a 1, 4 attachment. So now let's look at the 1, 4 addition. In the 1, 4 addition, instead of the nucleophile attacking here, the nucleophile attacks this carbon. Now, you would say, but the nucleophile shouldn't attack that carbon, because notice this carbon is not charged. But can't we draw a resonance structure? Now, watch when I draw this resonance structure. I can move this pair of electrons over and this pair of electrons up, giving this oxygen negative and this carbon positive. So this carbon is partially positive because of that resonance structure. Notice again how resonance structures play a part in explaining how this reaction takes place. So because we have a resonance structure where this carbon is partially positive, or totally positive actually, we can attack the nucleophile there. So if the nucleophile attacks there, this pair of electrons comes over and this pair of electrons goes up. Notice the product of that reaction. Now you have to keep track of your electrons. So now we have the C with the two H's attached. Now notice the nucleophile is attached back here. I'm not going to move any of my atoms so that I can keep track of everything. And now notice we have an O minus there and a CH3 there. Again, now we're going to protonate. So once we protonate this, notice we have this. And again, notice this is an enol. Okay, and we've seen these enols before. And when we have these enols, they tautomerize, which means this double bond comes here, and this H goes here. Notice the overall result is that the nucleophile and the H have added across the C double bond C. But in the initial step, notice the nucleophile added here and the H added here. And that's why they call it 1, 2, 3, 4. But we get the addition across the C double bond C with the nucleophile because of the tautomerism. So there's two reactions that occur. The nucleophile and the hydrogen add across the C double bond O, and the nucleophile and the carbon or the hydrogen add across the C double bond C. So on the test, if I asked you, what is the Michael product of this reaction? The Michael product is the one that comes from the 1,4 addition. So it's the addition across the C double bond C. That is the Michael addition reaction, okay? The 1,2 is what we would consider to be the normal product. So I could also ask on the test, give me the 1,2 and the 1,4 products of this reaction. Now, just a couple of reactions on page 11, or one reaction on page 11, to show you how this reaction actually is used in industry. Suppose you had a reaction and you wanted to make this compound. We wanted to make this compound. Now, if we look at this class of compounds, this is an alpha, beta, gamma, delta diketone. Now, why would we want to make this? Because then we could use it in a reaction where we deprotonated it and formed our ring and formed our condensation reactions. So how would we make such a compound using a Michael addition reaction? Watch what we're going to do. We're going to start with this compound here. Now, I would not expect you to be able to predict this reaction. But if I gave you the reactants, I would expect you to be able to predict the products, okay? Now, we're going to take this compound and react it with this methyl vinyl ketone. And I'm going to draw that structure out. Okay, so now let's react this. We're going to add a base. Now, it doesn't matter what base we add here, but in my notes, I added that one because notice we don't have any ester groups here. Now, what that base is going to do is pull off the most acidic hydrogen. And it turns out that this hydrogen is very acidic because remember, this CN group is very electron withdrawing. Okay, we learned that whenever we were doing our aromatic reactions. So this is the most acidic hydrogen. So what happens is, this is the first step. Now, what we've said all along is now this can act as a nucleophile. Doing what? Backside attacking in a Michael addition fashion. Okay, notice this is fairly bulky. So it would probably like to attack out here on the end. Okay, it's hard for it to get in here to the crowded part of the molecule. So notice this is going to attack here, kicking out here, kicking up here. Now let me redraw that product now. So notice I have a CH3 hooked to a C double bond O, hooked to a C, hooked to an H. I'm going to put my C triple bond N down here. Now notice what that's hooked to. A CH2 hooked to a CH, just following along, hooked to a C double bond O, CH3. Now this C double bond O is no longer a C double bond O because remember we kicked that pair of electrons up. Okay, so notice now I have this structure. If I acidify this, two things are going to happen. And this is where I hope you're seeing that you've learned a lot of chemistry. You just can't put it together yet. What does the acidification do? Most of y'all are going to agree it protonates that oxygen. Okay? Let's see, I think we have a double bond there. Whoops, I forgot that double bond. Remember that pair of electrons kicked up. So now what happens? It protonates that oxygen. But we also learned in chapter 21 that what that does is it takes that and turns it into a carboxylic acid. So now we've got CH2 hooked to a CH, double bonded to a C, OH, CH3. Now again, notice we have a keto-enol tautomerism here. So we can fix that to get that product. Again, notice what we have here. We have a carboxylic acid group. So we have a beta keto carboxylic acid. Didn't we learn from the malonic esters and the acetoacetic acid esters that we can remove that just by heating it? So notice whenever we heat that and lose the CO2, notice how we get that compound. So we can take something as simple as this, react it with something as simple as this, get this compound that we can then do a cyclization reaction to make another compound. So one of the things that these type of reactions allow you to see is that you can turn almost any functional group by going through a series of reactions into any other functional group. Now, the last reaction we're going to cover in this section is called the Robinson annulation. This is the same kind of reaction that we see here, but it's in a ring. And the reason this reaction is important is it allows us to make multi-ring systems. It allows us to make compounds that have multiple rings in them. And a lot of biological molecules, such as hormones and steroids and stuff, are polycyclic compounds. So we can use synthesis like this to make polycyclic compounds. Now I'm going to tell you there's a trick to the Robinson annulation. And here's the trick to it. No matter what compound you have, okay, it's going to have a C double bond O group attached to it. This one happens to have a methyl. And it's going to react with a conjugated system In this case, I'm using methyl vinyl ketone. The key thing to writing this reaction out is making sure that this C double bond O and this C double bond O are in line with each other. Okay, I guess I could actually move this one up just a little bit. That this C double bond O and this C double bond O are pointing in the same direction and that they're lined up. Now, this annulation is a reaction that is several steps. So again, what I would do is I would write out in steps what happens. This occurs in basic solution. Okay? The first thing that happens is the non-conjugated system loses a hydrogen. So there's a hydrogen here. Okay? So notice when we do this, it loses the top hydrogen. Now remember, all of these are equilibriums. So when we do this, notice what happens. Step one, it deprotonates, forming this. Now notice this is a nucleophile. It's going to do a Michael addition. So notice what happens. This attacks here, kicking this pair of electrons down and this pair of electrons out. That's exactly the same thing. So the second step is a Michael addition. Now let me redraw that. Now I'm going to try to draw this so that now that's connected there. There's that one, there's that one, there's my O, not a double bond anymore. And here's my CH3. Now let's keep track of the bonds. So here's this new bond that's forming. The double bond is now here, and the oxygen now has a negative charge. Okay, so isn't that the exact thing that happens in a Michael addition? Now we're going to protonate it. So the next step, let me go ahead and put this hydrogen on here just to keep track of things. Now I'm going to protonate it. But don't I have an enol? So now I'm going to, in the next step, do my tautomerism. So I put my double bond there and my H there. So what I have done at this stage of the game is I deprotonated this to get my nucleophile and then done my Michael addition. Nothing amazing there. Now the next step is we're going to deprotonate this again. Now we could deprotonate here, we could deprotonate here, or we could deprotonate here. It turns out that deprotonating here or here doesn't allow anything to happen. But when you deprotonate here, okay, so that's the next step. Deprotonate that bottom carbon. Once you deprotonate that, notice this is a nucleophile. But notice there's no double bond over here. So this has to just do a simple attack there, kicking out this pair of electrons. Now notice why this one is chosen, because that's going to give me a 6-membered ring. If I would have deprotonated this one and went there, I would have got a 3-membered ring. So that's not going to help. So now let me redraw this structure. So notice this is a very stepwise reaction. Now we're forming a new bond here. Now notice this carbon is this carbon. So now we have an O- on here. We still have a double bond O here. And we have a CH3 there. The next step is protonation. Now, if you look at this reaction, now what do we have? A alpha beta hydroxy ketone. Didn't we say that if we heat this compound, we can form a double bond? Now, going back to the original compound, let me go back to the original compound now. So here was what the original compound looks like. Notice we have a conjugated ketone reacting with a ketone. What do I get out of this reaction? A conjugated ketone. Can't I then take this, flip it upside down so that it looks like this, and react it with another ketone to add a third ring? And that third ring will still be a conjugated ketone. Then can't I add a fourth ring and a fifth ring? So I can make these polyring systems by choosing what R groups that were on the compound. I can vary the ring structure. So I can make synthetic hormones and synthetic steroids. And those are very important, okay? Because why? People need those. People need synthetic hormones in order to be able to live. You know, there's a whole industry based upon that. And then, of course, we all know the industry behind steroids. Some good industry, some good effects and some bad effects, okay? But it's based upon this type of reaction.